This video is sponsored by Audible. Nylon is an extremely important family of polymers that can be used to make a huge range of different products. It can be strung into fibers to make things like clothing and textiles, or molded into plastic parts and tools. Nylon was first used to make the bristles for toothbrushes, and it's still being used today. It's also used to make women's stockings, which have become known as just nylons. There are many forms of nylon, but the most common ones are nylon 6 and nylon 6/6. Each type of nylon gets its name from the length of its building blocks. For example, nylon 6/6 is made from 2 ingredients where each one has 6 carbons. Nylon 6, on the other hand, is made from just one 6-carbon chemical. There are other forms of nylon, like nylon 4/6 or nylon 610, but they're not as common. The different lengths of the building blocks gives the final polymer different properties, which makes them useful for different things. For example, nylon 610 is better at retaining its properties when wet, so it's the nylon of choice to make things like toothbrush bristles. Anyway, I decided to make nylon 6/6, and there's 2 major ways to do this. Industrially, adipic acid is first combined with hexamethylene diamine to form a nylon salt. The nylon salt is then heated, processed, and extruded as nylon 6/6. The other way is to first convert adipic acid to adipoyl chloride, and then react it with hexamethylene diamine. For this video, I've decided to go with the second method because it has a much prettier demonstration. However, I do plan to cover the industrial one sometime in the future. Okay, so to start things off, I need to convert the adipic acid to adipoyl chloride, and to do this, I'll be using 4 main chemicals: DCM, DMF, adipic acid, and oxalyl chloride. The adipic acid was made in a previous video, and I'll have a link in the description if you want to check it out. Instead of oxalyl chloride, it's possible to use other chlorinating agents like thionyl chloride, but they're a lot harder to get. A lot of them are listed as precursors under the Chemical Weapons Act, so they're not exactly the best thing to own. The adipic acid isn't super pure, so before getting started, I decided to clean it up a little. I dumped it all into a beaker, and then I added a whole bunch of distilled water. Although adipic acid isn't very soluble in water, we still don't want to add too much here. Before continuing, I quickly checked the pH, which came out to be around 3, which is expected for adipic acid. I made a solution of about 6 molar sodium hydroxide, and I started to add it slowly. The sodium hydroxide is a strong base, and it will quickly react with the adipic acid to form sodium adipate and water. Unlike adipic acid, sodium adipate is very soluble in water, so as we continue to add the sodium hydroxide, the solution should clear up. I know I'm done adding sodium hydroxide when I get a pH of around 7. All of the adipic acid should be in the form of sodium adipate, and the cloudiness here is due to impurities. The impurities that are present seem to be very small particles, which tend to easily pass through filter paper. So to get rid of them, I have to instead filter it through something called sea light, which is very similar to extremely fine sand. The solution passes through relatively slowly, but the stuff that I collect is crystal clear. Once everything has been filtered, I wash the beaker and the funnel with a little bit of distilled water. I again wait for all of this to pass through, then I take away the funnel and I drop in a stir bar. So now that I've cleaned things up a little bit, it's time to regenerate the adipic acid. To do this, I add 6 molar hydrochloric acid until I get to a pH of around 1. The hydrochloric acid reacts with sodium adipate to make adipic acid and sodium chloride. The sodium chloride is very soluble in water, but the adipic acid isn't, so it precipitates out. I continue adding the hydrochloric acid until I get to a pH of about 1. The beaker is placed in a freezer and cooled to around 5°C, and then the adipic acid is filtered off. The beaker is washed a few times with a small amount of distilled water. Once everything was pulled through, I turned off the vacuum and did one final and thorough washing. I turned the vacuum back on and I left it running for about 20 minutes to try to dry it up as much as possible. I scraped the adipic acid out of the filter and I let it dry for 2 days. When I came back, it was a relatively dry powder and I transferred it back to the original container. Okay, so now we're ready to do the actual reaction, and I start by dropping in a magnetic stir bar. I then add 5 grams of adipic acid, followed by 70 milliliters of dichloromethane. And the last ingredient is a small amount of dimethylformamide, which will be acting as a catalyst. I took away the funnel, and I replaced it with a vacuum adapter. Above the adapter, I attached a small addition funnel, and I added 11.6 milliliters of oxalate chloride. Oxalate chloride is a very dangerous and corrosive liquid, and you can see it fuming. It's a very strong chlorinating agent, and I do my best to avoid working with it. To the vacuum adapter, I attach some tubing which leads outside. This reaction produces a lot of hydrochloric acid gas as well as carbon monoxide, so this definitely cannot be done in a closed space. My workspace is extremely well ventilated, and I just added this tubing as an extra precaution. When I was ready to get things started, I turned on the magnetic stirring. Most of the adipic acid is not going to dissolve, and this is perfectly fine. I open the addition funnel, and the oxalate chloride is added over the course of about 5 minutes. My dichloromethane and adipic acid aren't perfectly dry, so there's a little bit of water present. The first little bit of oxalate chloride that's added is going to react with the water, and it can sometimes be pretty vigorous. It's highly unlikely that it would ever cause it to bubble out of the flask, but it's just a good precaution to take. Anyway, so as I said, the initial reaction is just with water, which produces hydrochloric acid gas, carbon monoxide, and carbon dioxide. Once it reacts with most of the water and gets rid of it, it will start to do what we actually want it to do, which is react with the adipic acid. When it does, it will convert the carboxylic acid groups to acyl chlorides and lead to the formation of adipoyl chloride. It will also produce carbon dioxide, carbon monoxide, and hydrochloric acid gas as side products. This is why it's really important to have good ventilation, because you really don't want to be breathing in hydrochloric acid or carbon monoxide. Because oxalate chloride reacts with water, and I want to make sure that all of the adipic acid is consumed, I need to use an excess of it. I used about twice the amount that was required, which assures that the reaction will go to completion, but it also means that oxalate chloride will be left over at the end. I'm now just going to quickly go over the mechanism. In the first step, the electrons on the nitrogen of DMF move to form a double bond. The other double bond opens up, and the electrons go to the oxygen. The free electrons of the oxygen then attack the carbonyl of oxalate chloride and open up the double bond. The electrons on the oxygen then move to reform the carbonyl, and the chloride is kicked off. The free chloride then swings back around and attacks the double bond. This leads to a cascade of electrons jumping around and the formation of the active Vilsmeier reagent. The carbon bonds in the oxalate chloride are broken apart, and it leads to the formation of carbon monoxide, carbon dioxide, and another chloride ion. The chloride then attacks adipic acid and pulls off an acidic hydrogen. The electrons shift, and the carbonyl is opened up. The free electrons on the oxygen then attack the Vilsmeier reagent and kick off a chloride. The chloride ion that's kicked off will then attack the carbonyl. A carbon-oxygen bond is broken, which regenerates our DMF catalyst and forms the final acid chloride product. The reaction is then repeated to the other side of adipic acid. After the last bit of oxalate chloride was added, it took about 3 hours for the adipic acid to completely disappear. During this period, the bubbling slowed down a lot, and the solution slowly became more and more yellow. Adipoyl chloride is slightly yellow, so this color change is a good sign. Eventually, all of the adipic acid was consumed, and there was no visible bubbling. From this point, the solution was stirred for another 24 hours. 24 hours later, the solution is significantly more yellow. It's also opaque due to impurities, which will need to be filtered off. To do this, I filter it through some sea light and glass wool. Before filtering through the actual solution, I wet the sea light and the glass wool with a little bit of DCM. It's important to use glass wool and not just regular cotton, because the oxalate chloride and the adipoyl chloride would probably destroy it. I tossed away the solvent that passed through, and then I started filtering the real thing. One thing to be aware of is that adipoyl chloride is sensitive to water, so it will react with moisture in the air. In theory, it's best to do this in a water-free environment, but I don't have one, so I tried to just filter it as fast as I could. One thing that's helpful is that we have excess oxalate chloride left over. Oxalate chloride is much more reactive, so in theory, it should be able to pick up the water and protect the adipoyl chloride. Once everything had passed through, a small amount of dichloromethane was used to wash the round bottom, as well as the funnel. When this was done, I took away the funnel and I dropped in a stir bar. Okay, now I need to get rid of all of the dichloromethane, as well as any unreacted oxalate chloride. And to do this, I set up a simple vacuum distillation. I set up a hot water bath, and with strong stirring, I slowly turn on the vacuum. It's really important to engage the vacuum slowly, otherwise it could bubble out of control. I continue with the distillation, and unfortunately, at some point it becomes opaque again. This isn't a huge deal, but it does mean that I have to do another filtration. Anyway, I keep going until it completely stops bubbling, and I'm left with this dark orange residue. In a previous run that I did, it didn't turn orange, and I just had a yellow liquid. I'm not exactly sure why there was such a difference here. In either case, though, I had a mixture of adipoyl chloride and a bunch of solid impurity. Unfortunately, most of the impurity comes from the dirty adipic acid that I started with. If I started with very pure adipic acid, I probably would have had relatively clean adipoyl chloride at this point. Anyway, it is what it is, and I now need to separate my adipoyl chloride from the other solid junk. To do this, I start by adding 50 grams of dry cyclohexane. The cyclohexane will dissolve the adipoyl chloride, but it won't dissolve the other stuff. After it's added, I put the stopper back in and I stir it for about 10 minutes. To filter it off, I do the exact same thing as before, where I pass it through sea light and glass wool. Before I pour it in, I wet things with about 2 grams of cyclohexane. Anyway, the cyclohexane solution is added to the funnel, and it slowly starts to filter through. At this point, we can see that the solution itself is yellow, and the orange color is coming from the solid stuff. I added as much as I could without including the solids to try to get it to filter through as fast as possible. Once almost everything had filtered through, I poured in the last bit that remained. The flask in the funnel was then washed twice, first with 10 grams of cyclohexane and then with 16 grams. In total, I used 78 grams of cyclohexane, which is almost exactly 100 milliliters. I wait for everything to pass through, and when it stops dripping, I take away the funnels and I cap the bottle. What I have now is roughly a 0.2 molar adipoyl chloride solution, which will be used directly to make the nylon. The solution is a little bit opaque because some of the adipoyl chloride reacted with water in the air and precipitated adipic acid. To make the nylon, I need to make a solution of hexamethylene diamine. When I open the bottle and take a look inside, it's completely solidified and it has formed some very nice crystals. With a lot of difficulty, I scraped out 4.4 grams and added it to a beaker. Hexamethylene diamine is quite corrosive, so it's important to wear gloves and be careful when handling it. I added 50 milliliters of distilled water and I stirred it until everything dissolved. Some of the flakes floated to the top, and started to zoom around, which I thought was pretty interesting. Anyway, once almost everything had dissolved, I topped it off to about 100 milliliters. With the hexamethylene diamine solution prepared, I'm ready to make the nylon. The adipoyl chloride seems to have gotten a little bit cloudier, but that's not really an issue. To make the nylon, it's pretty simple. I first add a little bit of hexamethylene diamine solution, and on top of this, I carefully add an equal amount of adipoyl chloride. The adipoyl chloride is dissolved in cyclohexanol, which doesn't mix with water, and it's less dense, so it floats on top. Because they're not mixed, the only place that polymerization can take place is at the interface between the two solvents. Using a pair of tweezers, I can pinch the nylon and pull it out of the beaker. The gooey string is wrapped around a glass stir rod, which I can then turn to pull out more nylon. What's interesting here is that the nylon I'm pulling out is not actually a string, it's more like a tube. The tube isn't hollow though, and it's often filled with hexamethylene diamine solution, so it's important to be careful when handling it. So now to talk a little bit about what's going on here. When the adipoyl chloride comes in contact with the hexamethylene diamine, it reacts to form an amide bond. However, on one end of this newly formed molecule, we have an acyl chloride, and on the other, we still have a free amine. So now the reaction can repeat itself, and it keeps doing this over and over to form a very large molecule known as a polymer. It looks like there's a whole bunch of nylon here, but it's a little bit deceiving because it's being puffed up a lot by the water that's being pulled up with it. It eventually runs out of either the hexamethylene diamine or the adipoyl chloride. When I squish it with my fingers, you can see that there's a lot of liquid with the nylon. To try to clean it, I dump it all into a water bath. Without destroying the nylon, I manually pull it apart to try to give it a better washing. After about 30 seconds, I just leave it there to soak, and I move on to making more nylon. I tried it again using the same amount of each ingredient, but this time in a much larger beaker. It ended up being pretty much the same thing, and the only difference was that it was a little bit faster. There's a larger surface area between the two layers, so we pull more nylon with each turn. It was a little bit tedious doing all this turning, so I tried to make things a little bit more automated. A glass stir rod was taped to an electric drill, so this time I just need to click a button to pull out the nylon. For this run, I decided to see what would happen if I just mixed the two layers together instead of pulling the nylon out. As I continue to stir, it slowly forms the nylon and turns into a somewhat disgusting mess. After about a minute of stirring, I'm left with an alien-like blob stuck to the end. When we take a closer look, we can see a whole bunch of air as well as liquid trapped inside. I then attempted to get creative by adding some fluorescein to the hexamethylene diamine. Fluorescein is a highly fluorescent molecule, especially under UV light. I actually made it in a previous video, and if you're interested in checking that out, there's a link in the description. I turn off the lights and I turn on my UV light, and then I carefully add the adipoyl chloride. Just like before, I use the tweezers to pull out some nylon. What's kind of cool is that we can tell how much water we're pulling up with the nylon based on how bright it fluoresces. At some point, I accidentally got the nylon stuck to the side of the beaker. At first it was a mistake, but it ended up being pretty interesting. In hindsight, I wish I put down the glass rod, and using my fingers, I probably could have pulled off a super thin sheet of nylon. In another run, I just poured in the adipoyl chloride and then did absolutely nothing. I left it for about an hour and I wanted to see what would happen if I just let it react passively. When I came back, the adipoyl chloride layer was no longer yellow. I poked around with a glass stir rod and tried to pull some nylon using tweezers, but it appeared that everything had reacted. What's interesting is the same amount of nylon has formed here as all of the other runs. In the other runs, when I pull it out using tweezers, it's an extremely thin layer and it makes it look like I'm pulling out a whole bunch of nylon. However, in reality, there's actually only a very small amount. For the last run, I used a lot more of each, and I thought it would take a while, so I used the drill as well. Near the end, it got super messy and was pretty gross looking. I ended up having to transfer the huge messy blob and restart with a fresh glass rod. The nylon from all of the runs was combined in the same bowl and given a thorough washing. Mixed with the nylon is a lot of unreacted adipoyl chloride, hexamethylene diamine, and also the fluorescein that I added in. After a thorough washing and having to change the water several times, I'm left with relatively clean-looking nylon. I personally didn't do it, but to clean things further, it might be an idea to do a dilute acid and a dilute base wash. Anyway, the nylon was taken out and squeezed tightly to get rid of as much water as possible. I then spread it out on some paper towel and let it dry for a couple days. When I came back, I had some nice and dry nylon with a mass of about 0.75 grams. It was a little bit tough, but still quite easy to break apart using my fingers. All of the nylon pieces were then shoved into a small test tube. I started blasting it with a heat gun, and the goal now is to completely melt it. The melting point of nylon is around 265 C, so this is going to take a lot of effort. It's also possible to use a Bunsen burner or a blowtorch, but I really didn't want to burn things. I occasionally had to stop and shove everything down to the bottom using a metal spatula. Once I got to the last little bit, I continued heating it until it completely liquefied. You'll notice here that there's some bubbling going on, and these are impurities that are boiling off. The major impurity is hexamethylene diamine, which boils around 205 C. The boiling eventually dies down a lot, and I decided that I was pretty much done. I allowed it to cool, and to get out the nylon, I smashed the test tube, which kind of exploded. I found the end piece that flew away, and this is the nylon that I got. Despite the fact that it was low quality and dirty, I was honestly impressed with it. The portion that was in contact with the test tube was very shiny and smooth, but the inside was a little bit bubbled up. After seeing what I made here, I decided that I would for sure make nylon the other way. The other way is a lot cleaner, and I should be able to get a much higher quality nylon out of it. A big thanks goes out to Audible for sponsoring this video and supporting my channel. Audible offers an unmatched array of content, including audiobooks, original audio shows, news, comedy, and much more. They're offering a 1-month free trial to all of my viewers, which you can get by going to audible.com/NileRed. It takes me a really long time to edit all my videos, and to keep me motivated, I usually listen to podcasts or audiobooks. I just finished listening to The Power of Habit by Charles Duhigg, and I definitely recommend checking it out. It's a very entertaining and informative look into how habit influences our lives and what we can do to change it. If that kind of book isn't your thing though, there's loads of other books you can listen to, like Game of Thrones or even chemistry textbooks. So if you want to help out my channel, you can sign up for your free trial at audible.com/NileRed and claim your free audiobook. So as usual, I'd like to thank everyone who's supporting me on Patreon. Everyone who supports me will see my videos 24 hours before I release them to YouTube. On top of this, all of my supporters can directly message me on Patreon with any questions or comments that they have. And I do my best to respond within about a day or so to all of my Patreon messages. If you support me with $5 or more, you'll get your name at the end of the video like you see here.